Okay, everybody, let's review the bipolar junction transistor-based amplifier today. I'm going to divide this into 4 parts. The first part will be some basic introduction. A bipolar junction transistor is a 3-terminal device. We can either have a NPN or PNP type of device. As can be seen, this transistor actually can be modeled like 2 diode or PN junction being put back to back or head to head together. And we are forming 2 junctions here. One is called emitter base junction, which is EBJ here. And the second one is called collector base junction, and CBJ here. Apparently, we cannot just simply put 2 diodes together to make a transistor. And also, even though the model looks like they are symmetric, but in the reality, they are not made in symmetric, which means the emitter and the collector are not interchangeable. The reason we can see that if you see the real cross view of an NPN bipolar junction transistor, and it will show that those emitter base and the collector, they are not symmetric. And in order to make a transistor to perform well, and this base region has to be very narrow. Probably we'll take another class to study how this transistor works. But here we are going to focus on how to make it as an amplifier. There are a couple of modes of operation for the BJT transistors. It depends on the binding condition of these 2 PN junctions, the EBJ and also the CBJ. There are 4 basic modes of operation here. So the first one, we call it cutoff mode. So in the cutoff mode, the EBJ is under reverse bias condition, and the CBJ is also under reverse bias condition. And both junctions are being reverse biased, and we expect no current flow. The transistor is totally shut off, so there's no current flow. The second mode is called active mode. In this active mode, the EBJ is being forward biased, and the CBJ is being reversely biased. And once we forward bias the EBJ, and we are going to generate some base to emitter current, that current actually will cause further collector current, even though the collect to base is being reverse biased. The third one is called saturation mode. So in the saturation mode, the EBJ is forward biased, and also the collect base junction is also forward biased. And in that way, we are going to saturate the transistor, and that's why we call it saturation mode. Reverse active mode actually is reverse bias the EBJ, but forward bias the CBJ. So that's like you interchange the emitter and also the collector, right? As in the active mode. It's still active mode, but it's a reverse active mode, and you'll see the performance is much worse than the active mode. And in digital logical application, the transistor will switch between the cutoff and also the saturation. But as a linear amplifier, it mainly works in the active mode. So due to the asymmetric construction of the transistor, so the reverse active mode is not working as the same as the active mode. Okay, let's focus on the active mode of BJT. So in the active mode, for example, if this is a NPN transistor in active mode. And in active mode, we will bias the EBJ at forward bias condition. So which means from base to the emitter, the PN junction actually will be cancelled by our bias voltage. On the other hand, the CBJ will form a reverse bias condition and will give us a depletion region. So in the depletion region, we will form an electrical field. And in this electrical field, so the right-hand side will be positive, and the left-hand side will be a negative charge. And that will form an electrical field there. When we forward bias the EBJ, and we are going to inject the holes to the emitter, and also the electron will be injected from the emitter to the base. So the electron will diffuse in the base region. If the base is narrow enough, and when the electron get into the base and when diffuse to the boundary of the CBJ, because now CBJ is reverse biased, and then we have this kind of electrical field, this electrical field will drive the electron and quickly goes into the collector side, which forms the collector current. Now this current actually is going to be much stronger than the injection current we injected from the base. Now this is the mechanism how the transistor will amplify the current. We inject a very small current to the base and then to the emitter, and the electron will get into the base and then being swiped by the CBJ junction or the electrical field formed there and into the collector and then form the collector current. So this is basically how the transistor work. As we can see, we can not only simply put two diodes together like a back-to-back to form a NPN junction, because we do require this layer of the base layer needed to be thin enough in order to allow electron to quickly diffuse to the boundary and being swiped to the other side of the collector side to form a significantly bigger collector current. Now here I list a few fundamental formulas that can describe the active mode of BJT. So the first equation is RE equals RC plus RB, which tells us that the emitter current will be the summation of the collector current and the base current. And the second equation tells us the relationship between the collector current and the base current. And if we go back to the figure, we can see here the emitter current is going to be much larger than the base current. But the emitter current is also larger than the collector current. And the alpha will describe this relationship. Apparently this alpha has to be smaller than 1, but could be very close to 1, because the amplification from the base current to the collector current is very big. So now we can also find out the base current and the emitter current relationship from this formula here. So the fourth equation gives us the relationship between the collector current and also the base current, and which this beta here actually is the gain, right? Is the how much current we are being amplified from the base to the collector. And this alpha and the beta, both of them are gain, but alpha is a number close to 1 but less than 1. Beta is going to be a beta number. So the fifth equation tells us this relationship between alpha and beta, and also the same way as the last equation. For a typical silicon-based BJT, and its VBE is approximately about 2.7 volts, just the same as we described in the diode. So the VEB is also the same thing as 0.7 volts. That's the built-in potential, the voltage we need to apply from the base to emitter in order to cancel this built-in potential. To categorize the performance of the transistor, and we can get IV characteristics. And here's an example for the common emitter IV characteristics. So the horizontal one will be the voltage between the collector and the emitter, and the vertical line is the collector current. And we have a different line here. Each line represents a different base current. If we give a different base current, then it's going to be amplified by a number of beta, and then give us the collector current. This is the NPN transistor. This current actually can be described by this equation here. We can use a hybrid pi model to describe this DC characteristics. So this is called a large signal equivalent circuits model at a common emitter configuration. Now this transistor can be either modeled as a voltage controlled current source, or can be modeled as a current controlled and current source. Now, even though the transistor itself physically is a current controlled current source. From this DC characteristics, we can see the two working regions here, and apparently in this region will be the active region, and the collector current will change with the number of beta of the base current. And in this region, and we call it saturation region. In the saturation region, and both of the junction will be forward biased, and in that case, when we increase our collector and to emitter voltage, we will see the current increases. No, the previous one we see the current is being, the collector current is being amplified by a number of beta and give us a flat DC characteristics. But in the reality, and we are not able to get that. And in reality, this curve will actually is what we get. Now we see a small slope on each curve. So if we extend this curve, it will merge at one point, and this point, and we call it early voltage point. And this early voltage, this early effect, will introduce some additional things to the performance of the transistor. And now we can see the collector current is being governed by not only the base current, but also this number of VA here, right? So this will introduce another characteristics of the transistor, which is called output resistance. And later on we will show that this actually will change the output resistance of the transistor. And we can define the output resistance of the transistor by this formula here. Right, so 1 over Ro, that is the conductance, right? The conductance is defined by the change of this current divided by the change of this voltage, and we can also easily to calculate this Ro if we can find a specific point, ending point, if we specify the current, the capital R C here, and that will, if we know the number of VA, and we will be able to calculate at that particular point the output resistance of small Ro. As we can see here, at a different location, this Ro will be different. That is because is capital R is C dependent, the DC current, right? This current changes will give us the different value of this output resistance, because our VA number usually does not change. For example, for a typical silicon-based transistor, our VA number is about 100 volts, and we can get like the output resistance about 100 kilo ohm at RC equals 1 milliamps, and about 10 kilo ohm when IC equals 10 milliamps. In order to make the transistor to work as an amplifier, and we need to make it working at a certain point, like a certain biasing point. But how to analyze this biasing point? For example, I have this circuit. Now this is a common emitter circuit, or common emitter configuration. If we look at the base input side, and we are going to have our bias voltage VBB here. And this VBB will put this base to emitter junction in the forward biased condition. Then we are going to send in current capital RB into the circuit. And then we have this RB resistor here will regulate the current, right? But how much current we can get into this base? We know this base to emitter junction is a diode behavior, right? If we do the DC characteristics, we will be able to get this DC diode behavior characteristics. In order to find out where's the exact biasing point, or we call it quiescent point, or working point of this common emitter configuration, and we can rely on the load line equation. Now, in order to get the load line equation, we do the same thing as we did in the diode. We can apply a KVL, and from the biasing voltage and through this resistor, and then through the EBJ here. Now this biasing point, this loop, actually, if we apply a KVL, and we are going to get our load line equation. So the current flow through in this loop can be calculated by the voltage difference and between here and here across this resistor. And here the voltage is VBB, and here is the voltage we need to turn on the EBJ, which is the VBE. Now the voltage difference divided by the resistance value will give us the current. Now this is the current equation. Assume we don't know where exactly is our VBE, and then we can let this VBE change along this x direction, and then we'll be able to get a straight line, which is we call it a load line. Apparently the slope of this load line equals negative 1 over RB here. Now this load line will have an intersection point with the DC characteristics of the diode, or the EBJ here. Now this point will determine our working point, which means only this point will allow this loop to work, right? This loop only works at this point. This gives us the VBQ here, the EBJ voltage, and also gives us how much current, and we call it RBQ, how much current get into the base. Now using this graphical approach, and we will be able to figure out where is our DC bias point at the base. And we can also use the graphical approach to figure out what's the biasing point at the collector side. Now this is the curve we get, the DC characteristics of our transistor. And again, we can apply the same KVL rule and in this branch from VCC to the ground. From VCC to the ground, we have a voltage drop across this RC here. And then and then we have this VCE voltage. And this VCE voltage is the voltage between the collector and also the emitter, because the emitter is grounded already. And from the DC characteristics, from the previous analysis, we will be able to figure out and how much is our base current, which is IB here. Now this IB will give us a single curve, which is the IC curve, will change with respect to the change of this VCE here. But we don't know how much exactly and VCE is. And we can build another load line equation. Now this load line equation is based on this KVL equation here, with the voltage applied here and then how much current goes through, and this current can be calculated by the voltage drop across this resistor, this IC, and VCC minus VCE here will give us the voltage drop across this RC and divided by RC. And then this equation, if you are thinking this VCE is a variable which can be changed, and then we can get a straight line. Now this straight line will have an intersection point with this IV characteristics of the transistor at this RB level. And this point actually is our DC biasing point at the base side. And this will give us not only the VCEQ, so this is the VC, the voltage between the collector and the emitter, and also tell us the current flow into the collector, which is called ICQ here. And how can we make an amplifier and based on this bipolar junction transistor? And here is how it works. If we are be able to properly bias the transistor, as we can see here, then if we are be able to send a small signal at the base, and here, probably you cannot see that, if we send in a very small sine wave at the voltage sine wave at the base, this small change of the sine wave or voltage signal will cause a current change, right? So the base current is going to change. Well, this current will go along this IV characteristic of this EBJ. Now this change will be will happen along this line. This line actually is a slope, can be defined as 1 over R pi here. Now we're going to talk about more about this R pi. This R pi actually is the slope of this EBJ characteristics at that particular point. Now this is the working point at that particular point. And give us a varying current at the base current. Now when the base current is changing or is varying, now when the base current is changing, now we can see the IV characteristics of this transistor now is also changing. It will change from this line to this line, right? When the signal is changing. Now when this current is changing, this is the IC current apparently is changing. Now this IC current is changing will cause the voltage drop across the collector and the emitter also change. Now this will give us a larger change, a voltage change. Now we can see BJT can working as an amplifier to amplify a voltage signal, even though the BJT itself is a current controlled, a current source, but we will be able to amplify a voltage signal by constructing these circuits or properly bias the transistor. And we have two terms to define the performance of the amplifier we just analyzed. The one term is called transconductance. And the transconductance is defined. Now, if we plot x-axis, this x-axis as the VBE, the voltage change between the base and the emitter, and we plot the vertical axis as the collector current. Now we have this current versus voltage change. And we have our working point, right? This working point, our VBQ, we just analyzed, and the ICQ we get. And we know when the base voltage is changing, and then we are going to get a current changing, right? So the current will change along this line. Now this line gives us a slope, right? This is a tangential line to this curve. Now this slope is defined as Gm, which we can find the partial derivative with respect to this VBE at this particular point, and we get this transconductance term. So the next term is called a voltage gain, and how much voltage we amplified. And this voltage gain is defined by another characteristics. And now we plot the x-axis still the VBE, but the y-axis becomes our VC here, or VCE here. As from this curve, we can see we still have this Q point, but when we change our VBE, and then our voltage will change or give us amplified signal. Apparently, we can define the slope here as AV. AV is being defined as dVc divided by dVi, which is the input voltage here, and how the voltage change. And this will give us the voltage gain. Okay, this is the basic introduction to bipolar junction transistor using for signal amplifiers. And in next part, I'm going to give you some introduction on how to analyze this amplifier based on the small signal analysis.